is made up of particles in motion was originally a scientific hypothesis that was proposed to explain a lot of the things we've observed about matter. And it's called the kinetic molecular theory of matter. So this underpins pretty much everything that we think about how matter behaves. Let's go back for a second to that whole concept of how we work with science. So, theory in science is what? No. Theory is a really high bar. Theory is about the highest bar in terms of explanations. So we can have a hypothesis to explain, and a hypothesis is a working explanation. This is how we believe this works. When repeated observations all support a hypothesis, then we begin to describe that as a theory. So right now in physics we have string theory. In biology we have, string theory may not be a good example. It's still a little bit tenuous. But we've had enough observations thus far. Oh, I can't even, I'm completely not qualified to explain it to you. I mean, it is so far above my pay grade, I can't even. Stuff.
Are theories the things that can't be turned into laws?
Yeah, theories don't turn into laws. Laws don't explain anything, they just describe. Question?
Can I go to the office?
Yes, go to the office. Laws, like law of gravity, law of gravitational attraction, doesn't explain why gravity works. As far as the law of gravitational attraction is concerned, gravity could work because there are invisible rubber bands around your ankles. Laws don't explain how things work. Theories do. So the theory of the kinetic molecular theory of matter explains how matter behaves. And it's a solid theory. It's something where we haven't had any observations that would contradict the kinetic molecular theory of matter. So not a law, not a hypothesis, a theory. Pretty high bar. Theory is pretty serious stuff. This is not like, oh, I have a theory about what's going to be for lunch today. No. That's colloquial use. Okay. Within the kinetic molecular theory of matter, which we're going to discuss from here on out, is just Km. We can talk, yeah, it's much easier. We can talk about the behavior of any kind of matter, but here, of course, as we're talking about gases, we're going to focus on gases. And we make some assumptions, and we describe this perfect gas, this ideal gas. So if you think back to ideal stoichiometric calculations, what did they describe? Ideal stoichiometric calculations. What was so special about them?
Well, if everything went right.
Everything's perfect! It's all perfect. An ideal gas is this imaginary gas. There is no such thing as an ideal gas. It doesn't exist. That perfectly 100% conforms to all the assumptions we make about kinetic molecular theory. So very often in physics, and this is physics really, it's where physics and chemistry meet and kiss and part ways. In physics, very often we make assumptions about systems that aren't quite reflective of the real world, but in order to do the math, we have to. So, in chemistry, in this portion of chemistry, we talk about the kinetics of gases. And to do that, we have to talk about ideal gases, which are, again, like I said, they don't exist, but things that behave perfectly, and things that, there are 5 assumptions that we make about the way the gases behave. So let's start with those. Lots of particles, very far apart. And this gets to something a lot of you said about they're spread out, they're loosely knit, they're not very dense, all those things. They're made up of lots of particles, but there's a lot of empty space. So I would like you to once again take your hands. We're going to conduct a small experiment. I would like you to place them up in front of you like this. And I would like you to now smack the desk. Smack, smack, smack. Keep smacking. Keep smacking, keep smacking. Okay, wonderful. Now, what I would like you to do is, I would like you to put your hands up like this in the air. And I would like you to, as hard and fast as you can,
Person next to you.
no, sadly, smack the air. Come on, smack the air. Smack it, smack it, smack it, smack it. Oh, come on. This is going to be on YouTube. Okay. Okay, so what differences do you note?
They're just stinging.
You stop.
You don't stop.
Okay, so nothing there. That's exactly the wrong thing that I was hoping somebody would say. Perfect. Okay, when you strike the desk, it hurts your hand. If you hit it hard enough, it hurts your hand. You're striking a whole bunch of particles. They're moving, but they're packed very closely together. When you're striking the air, you are striking particles, but they're very spread out. There's a lot of empty space in between them. So it's not that you're striking nothing. If you fan yourself like this, now that you've exerted yourself so much smacking the air in the desk, you're moving what you feel, the breeze against your face. You're moving particles. What you feel is actual particles striking you. So gases are made of particles, but they're pretty spread out. And that means we can compress them. So we can have you ever pumped up a tire on a bicycle or a vehicle of any sort? Okay. You're compressing air and putting it into a container. That's all you're doing. So, and that's because there's so much space in between air molecules, air particles, that we can compress them. Okay. This is where we have to talk about a physics term. Oh, elastic. What does elastic mean to you? Stretchy. Okay. In physics, we talk about elastic and inelastic collisions. In an elastic collision, two things bump into one another, and when they separate, they each have the same amount of kinetic energy they had going in. They may have traded it, so they may be going in different directions. So let's imagine bumper cars. So I'm going to put you and you in two bumper cars, headed nose for nose at one another at top bumper car speed, which is not all that fast. Okay. When you two strike, no. What's going to happen? You're going to bounce straight backwards. We're going to laugh. You're going to get a little bit of whiplash.
Maybe a concussion.
No concussions, please. In a perfectly 100% elastic collision, the amount of energy of motion, kinetic energy that you had coming in, and the amount that you had coming in, you have going out. Now you're headed in opposite directions. You've traded energy in essence, but you haven't lost any. Okay, that is a perfectly 100% elastic collision. When we're talking about gases, when we're talking about molecules in general, we're talking about collisions, there are particles running into one another all the time in gases and in fluids. What we pretend is that all of those collisions are perfectly elastic. That as long as the temperature doesn't change, the total amount of kinetic energy doesn't change. And we're going to talk more about the link between temperature and kinetic energy in a little bit. Okay. This is the part that you've been familiar with since, probably the 3rd grade. Particles are in constant motion. And because they're in constant motion, they have kinetic energy. So, here's the other thing we assume. Now, I'm going to put you and you on roller skates. Can you roller skate? Good. Can you roller skate, Francis? Awesome. So I'm going to put you at the opposite ends of the hall, and I'm going to send you hurtling towards one another on your roller skates.
We actually do these experiments.
No, it's a thought experiment.
But I can see. If I
On
see
your
it
own
better,
time.
I'll learn it better.
On your own time. Okay, so they're both in motion on their skates. They have kinetic energy, yes? Now, they're friends. They would love to not be hurtling on their skates down the hall at breakneck speed towards, I don't know what sort of dangers await you. It would be great if as they pass, they could grab onto one another and stop and just wonder what the heck just happened. But they're going so fast. They've got so much kinetic energy. There's no way they can possibly grab a hold. So what we assume about gases is that their kinetic energy is so high that if there are any little forces of attraction between the molecules, they're overcome. They're moving too fast, they don't slow down. Do you understand that all objects have gravitational forces of attraction between them?
So like these two desks.
Has that been explained?
Yes.
Yes. Now, in the case of these two desks, why aren't they inching together? Because the pull of the Earth is so much more massive. But if we put these two desks out in the vacuum of space far away from the Earth, they would be attracted to one another. And the same thing happens at the molecular level. There are little forces of attraction. But what we assume is that gases have high enough kinetic energies on their own that completely is overshot. Just like these desks are completely overshot by the gravitational attraction of the Earth, they're not being attracted to one another because they're overshadowed by this other force. Okay, the big exception to this is if we get gases cold enough, they're going to start to condense out and turn into liquids. What happens when a gas turns into a liquid? Well, okay, it gets cold, then it turns into a liquid, but at a molecular level, what happens when we have a gas? We have all these little gas particles zipping around. They slow down, they get closer together. What is condensation? Okay. Well, describe it to me in layman's terms. You don't have to give me a scientific textbook definition. We have a gas, and whatever that gas is condenses and becomes a liquid. So those particles go from moving around so fast that they can't possibly catch one another to moving slow enough and being close enough together that they can catch one another and turn into a liquid. That's condensation. So we assume that they've got enough Ke to shoot right past one another except when we get them down close to the point where they're going to condense. And then those forces of attraction overcome their kinetic energy. I'm going to pause the video.